Hello everyone. In today's unit, we'll explore green and efficient built environments. I'm Ismat Fati, working as a clean construction manager for C40 cities. Responsible for almost 40% of all greenhouse gas emissions, the built environment is fast becoming a driving force behind global climate change mitigation efforts. By achieving net zero emissions through circular construction, passive design principles, and integrated net zero design strategies, neighborhoods and building designs can contribute to moving towards green and energy efficient built environments. These strategies contribute to SDG 7, affordable and clean energy, SDG 11, sustainable cities and communities, and SDG 13, climate action. The presentation is divided into three main parts. Part 1 is providing tools for implementing clean and circular construction. Part 2 is on reducing building energy consumption with passive design principles. And Part 3 provide tips to design net zero buildings. We will conclude with lessons learned. Let's start with Part 1 in understanding how to implement clean and circular construction. The C40 clean construction hierarchy, as shown in the image, serves as an organizational framework for within the sector to adopt clean and circular construction actions. The hierarchy steps are organized from top to bottom according to their potential to reduce emissions, and from bottom to top according to their impact on improving the city air, noise and soil pollution and other health issues. Depending on the context, any of these 4 steps can be used as an entry point. However, the earlier stages of the construction projects have the greatest potential for emission reduction and cost effectiveness, making it critical to consider embodied emissions from an early stage of planning and design. Let's unpack these 4 steps in the upcoming slides. The first step of C40 clean construction hierarchy is to prioritize existing buildings and infrastructure. All constructions, both new assets and retrofits, will add embodied emissions to the neighborhood emissions. This step includes optimizing, reusing and repurposing building and infrastructure or underutilized space to minimize this impact. Using an existing asset for multiple purposes will reduce the need for new construction and dramatically reduces the need for virgin materials and upfront emissions. Opportunities for infill development, adaptations, renovations will vary according to the neighborhood. An example is the former headquarters of BBC Television. They have been turned into a mixed-use residential, commercial and leisure complex while retaining the heritage buildings. The second step of the C40 clean construction hierarchy is to use materials efficiently and to switch to low carbon and local alternatives. It applies to existing assets as much as to new construction once the latter has been deemed necessary. Fostering material efficiency challenges the current construction practices, which more often than not use far more virgin materials than structurally required. The idea here is then to use right amount of materials and the right type of materials as structurally needed through material reuse and switching to low carbon alternatives. Timber and other bio-based materials and low carbon concrete all have low carbon impacts. An example is the Rwanda Institute for Conservation Agriculture. The project prioritized low embodied and natural and local materials such as stone foundation, earth walls and timber roofs. These design decisions led to 96% of materials by weight being sourced in Rwanda, contributing to a 60% reduction in embodied carbon. The third step of the clean construction hierarchy is to plan, design, and build for the future. It applies to existing assets and new construction and is all about ensuring that our built environment is not only low carbon or regenerative but also fit for the future. This implies that what is built now should, by design, facilitate material recovery and reuse and withstand future climate shocks. Where construction is required, asset lifespans can be extended by embedding flexibility and adaptability so that the use of assets can respond to the future needs of residents, workers, and visitors. For instance, the design of maternity waiting village in Kasungu, Malawi breaks the singular block into series of smaller components clustered around small courtyards. This plan borrows design cues from the vernacular layout of the Malawian villages. Transformative opportunities at neighborhood level include material storage and reuse across plots and ownership boundaries. Neighborhoods can pilot the development of circular construction hubs where reusable construction materials can be stocked and made available. In Vienna Seascard development, for instance, 1 million tons of excavated earth and aggregates were sourced, cleaned, and crushed on site for the construction of 3,000 new housing units. Integrating modular and reusable components and designing for deconstruction supports circularity. Designing for circularity includes building in layers, minimizing waste, and ensuring adaptability over time, and selecting materials with lower life cycle emissions impact. Another interesting example on bioclimatic homes using local materials and modular construction is by the same architect in Auroville in India, where a neighborhood prototype for collective living promotes community and sharing. Using insulating terracotta roofing units on part prefab beams, they were assembled as an easy modular construction having high insulation properties. Public spaces in this design are distributed for different scales of grouping with a hierarchy that includes intimacy. The last step of the clean construction hierarchy is transitioning towards clean and safe construction sites. Efficient construction processes include optimizing logistics and switching to zero carbon vehicles and machinery. These actions reduce direct emissions impact. They also improve air quality, reduce noise pollution, and minimize waste. New construction and deconstruction techniques provide opportunities for new skills and jobs. Moving on to part 2 of a presentation, reducing building energy needs with passive design principles. Designing climate responsive buildings uses bioclimatic and passive design approaches which reduces buildings' energy needs. Buildings interact efficiently with site and the climate through their shape and orientation, the airflows, the treatment of facades, the thickness, and the design of the envelopes, including the form of relationships between the exterior and the interior. Solar, water, and green spaces enhance user comfort and pleasure for the residents. Traditional buildings in Indonesia, for example, are roof architecture. The height from roof ceiling to the floor avoids the heat transfer through radiation, while hot air moves upwards and escapes to the roof porous materials. Walls are made of natural breathing materials like timber and bamboo so that the air can flow in the rooms. The large overhanging roof shade the veranda and the walls. In the hot and dry climate of Morocco, the traditional courtyard house creates a microclimate through clear surfaces reflecting the heat. Cool breezes then enter the courtyard and water cooling. Opposite to what we've just heard, in the cold climates, the goal here is to maximize the warming benefits of solar radiation while minimizing the impact of winter winds. Strategies include orientation and adding sun spaces to absorb the sun's heat, store it, and transfer it to adjusting rooms, as shown here in Viki in Finland. Moreover, the design blocks the wind and avoids wind penetration with gradual height transitions and with inner protected courtyards, as shown here in Malmo. In hot and dry regions, buildings are open and constantly ventilated naturally. They are not very compact and often combine open and closed spaces. The walls are light and have many openings and vents near the floor and ceiling, creating a pressure difference, causing air circulation and constant ventilation. Moreover, in these buildings, the roofs are well insulated and light colored with a reflective coating. Shading elements such as awnings and roof overhangs minimize solar radiation on facades, and louvers or shutter windows which facilitate continuous airflows. Ceiling fans increase comfort during temperature peaks. An example is the microtropicality house designed by RAD plus AR in Indonesia. Variation of space volumes allows to create constant temperature and pressure differences. The multi-layered facade reduces radiation, directs the breeze inside, shades the windows, and cools the walls. The dwelling promotes an environmentally friendly and healthy lifestyle. In hot and dry climate zones, passive design takes advantage of the huge temperature difference between day and night. Thermal mass of exterior walls and roofs absorbs the heat slowly during the day and slowly releases it during the night. Openings for natural ventilation are provided to cool the inner structure during the night time. Natural or artificial shaders like awnings, overhangs, and louvers then control the solar radiation. An example is the primary school in Mali's Dugon region. The design uses vernacular techniques with thick walls made of local earth. Thanks to their thermal inertia, the night coolness is diffused during the day by thermal dephasing. The windows are protected from direct sunlight by galleries that make walking pleasant while allowing solar interaction. Another example includes the wind tower, which is a traditional architectural element used to create cross ventilation and passive cooling. They have been widely used for the past 3,000 years in North Africa and West Asia, for example in Iran. The early 21st century saw them used again to increase ventilation, cut power demand for air conditioning. An example is the University of Qatar in Doha. Wind towers ventilate living spaces by capturing the high winds. They create a pressure difference between the top and the bottom of the tower. A double duct allows the warm air accumulated in the house to rise while the cooler air brought by the light wind at the top is drawn down. In this last section, we will touch upon designing for net zero buildings. It is international scientific consensus that to prevent the worst climate damages, global net human caused emissions of carbon dioxide need to fall by about 45% from 2010 levels by 2030, reaching net zero around 2050. To go net zero is to reduce greenhouse gas emissions and to ensure that any ongoing emissions are balanced by removal. An example is the French dream town Nadenpat in Hangzhou, China. It provides more than twice as much as renewable energy than its consumption. So what do we mean by a net zero building? A net zero carbon building, by definition, is when the amount of carbon emissions associated with the building's product and construction stages up to practical completion is zero or negative. Through the steps explained above, the use of offsets where no other solutions can be found, or the net export of on-site renewable energy. Historically, design decisions regarding material choice, material volumes, buildings lifespan, etc. have typically been made with a heavy focus on operational emissions and aesthetics without considering the embodied emissions. Moreover, in many cases, increase in renewable energy production and existing energy efficiency regulations means that the operational emissions of buildings are already set to decrease. The neglected embodied emissions are set to rise and should be pursued as part of the whole life cycle approach to carbon reduction. A net zero whole life carbon building will then minimize on site embodied carbon and compensate for all the residual emissions in the supply chain, in addition to the measures targeted by a net zero carbon building. A whole life cycle approach is the way forward which captures all life cycle stages, quantifying the embodied and operational emissions of a building or infrastructure project over its entire lifetime. Built by the Shanghai Construction Group, the SCG0 Plus project by Decibel Architecture is said to be China's first 5-0 building, meaning zero carbon, zero energy, zero water, zero waste, and zero formaldehyde. The designers have incorporated prefabrication methods in structure and facade assemblies and robotic fabrication techniques. They've used innovative low embodied energy materials such as recycled steel, low carbon concrete, and cross laminated bamboo. They've implemented rainwater and solar energy capture systems. It's time to conclude the presentations with some of the important lessons learned. The three main takeaways we want you to go with is: first one, the embodied emissions in building can be reduced by maximizing its existing assets, optimizing and repurposing existing buildings, infrastructure, and underutilized space. Second, circular processes include sourcing local materials and building for disassembly and reassembly. Lastly, operational energy can be reduced by design and passive bioclimatic techniques adapted to different geographies, climates, local building culture, and building use. Thank you for watching the presentation and hope you found the information useful.